We introduce FlameForge, a unified volumetric fire and combustion framework that supports the simulation of general wooden structures capturing the multiphase combustion of charring materials. We first illustrate its capabilities by simulating the fire spread and combustion using a model of a traditional Chinese boat which has been fully made out of wood. After the ignition at the bottom, the fire spreads quickly to the roof and further progresses before the whole boat burns brightly. The handling of a more complex geometry is shown by simulating a burning watchtower with different ignition locations. The fire starts at the roof such as after a lightning strike, from the side using a flamethrower, or at the bottom of the tower such as due to vandalism. The simulator can also capture the fire spread across multiple objects. In this scene, a tree is on fire which spreads further due to the wind field, igniting the roof of the house nearby causing severe damage. In contrast, if almost no wind is present, we can solely observe the burning tree as the house remains untouched. Different types of wood, as well as non-charring materials such as acrylic glass or non-combustible materials such as stone, can also be handled by our FlameForge simulator. These features are showcased by burning down a house which is composed of two types of wood, corresponding to the walls and roof, non-charring acrylic windows, and a non-combustible chimney made out of stone. The roof catches fire causing smoke development and fire spread. After some time, the relatively thin wood of the roof has already been burned while the thick walls are barely touched. The chimney made out of stone still remains intact at later stages. We are quantitatively validating our simulator by comparing it to physical combustion experiments. This kind of combustion experiment usually requires a large scale, as seen here in the experiment by the National Institute of Standards and Technology. Since we do not have the resources to perform such kind of a large-scale experiment, we developed a small-scale tabletop experimental setup. We designed a small device that records the weight of a small sample and the temperature at 4 different locations. We burned the samples inside a preheated chamber to emulate the conditions inside a larger-scale fire. Here are 2 time-lapse videos of the combustion of a charring material, beechwood, and a non-charring material, acrylic glass or PMA. In the beechwood case, the combustion starts violently and the sample loses mass quickly. After a few minutes, however, a charred layer has formed and the combustion rate is slowing down significantly. Only slowly burying char is left toward the end of the combustion process. In sharp contrast, the non-charring PMA sustains its high combustion rate over the complete combustion process without slowing down. The graph on the left shows the measured and the simulated mass. Our simulator can accurately capture the behavior of the charring and the non-charring material.
As fracture mechanics plays a crucial role in the accuracy and reliability of combustion simulations, we exemplify the potential for two-way coupling between our simulator and additional mechanical simulators. In particular, we simulate a fire scenario at the historic wooden King Louis Railway Bridge, which has been built by the Royal Bavarian State Railways from 1847 to 1851. It is spanning the Iller River in the town of Kempten, located in Algovia, a region in Swabia, southern Germany. It is regarded as the oldest surviving bridge erected by the renowned American bridge builder William Howe. Although presently supported by a steel composite construction and used as a pedestrian and bicycle bridge, it has originally been constructed by 3 different types of wood, larch, oak, and pine, as well as iron and stone. Based on 2D construction drawings, we have remodeled the complete bridge using these materials. Originally, this bridge has been encased to shield the wood from weather elements, and likely also to safeguard it from glowing pieces of coal that might have fallen from locomotives for fire protection. We simulate such a scenario where glowing fragments fall onto railroad ties, sparking a strong fire. The fire damages the supporting structures, causing the bridge to deform. The characteristic sagging effect can be observed. The fire further intensifies until it can eventually be extinguished. As the fire is almost extinguished, the bridge's central element has been severely damaged, while the tracks are finally drooping in the form of a catenoid. Ultimately, the fire causes such severe damage to the King Louis Railway Bridge, recognized as a historical landmark of civil engineering by the Federal Chamber of Engineers in Germany in 2012, that its central element would have to be entirely demolished and rebuilt.
Thank you for your interest in our work and watching this video.